This video is about pulse width modulation, often abbreviated PWM. It corresponds to section 35.2 of the textbook Applied Analog Electronics. Pulse width modulation is something that is used for encoding signals. We've looked at two basic encodings of signals so far, and that is analog and digital. For analog signals, our time was continuous, and for digital signals, our time was discrete. Our values for analog were continuous, and for digital they were discrete, generally 2 to the n for some number of bits n. PWM has discrete time. It has continuous values, and it has only two voltages. Now wait a second, you say. How can it be continuous values with only two voltages? I mean, the analog stuff, we had, to get continuous values, we had continuous voltages. There was anything between the low voltage and the high voltage was possible. For digital, we had discrete voltage values, or numbers, that corresponded to different voltage values. And if we had 16 bits, we had 2 to the 16th different discrete values, different voltages that were being represented. But for PWM, I'm claiming continuous values, but only two voltages. Well, let's take a look at what's going on with signal. So let's look at some intervals here of time, delta t. Draw some tick marks here that correspond to, each one of these is an interval of delta t time. Now, if we were looking at a digital signal coming out of an analog to digital converter, what we would have is, digital to analog converter, so take the digital signal, convert it to analog, we would end up with a voltage here that was constant for that time interval that was one period of our delta t. For PWM, we do something different. We only have two values. Let's call them 1 and 0. And what we do is we spend some time at 1 and the rest of the time at 0. Some time at 1, the rest of the time at 0. Some time at 1, the rest of the time at 0. What is the average value of the voltage within this delta t period? Well, let's say that the time it's high is d times delta t. So the average value there is going to be d delta t times v high plus 1 minus d times delta t v low. So this much time at the high voltage, this much time at the low voltage, divided by the total time in that interval. Notice that all the delta t's here cancel, and so this is just equal to dv high plus 1 minus d v low. That's the average value. Notice that d is continuous. It's not restricted to being just 0 or 1. It can be anything between 0 and 1. So our voltage value, our average voltage value for this time period is continuous. So we have a continuous value, but only two voltages. And this is really the secret to pulse width modulation, is we can get continuous values while only having two voltages. The advantage of that is that having a 2-voltage system is very, very easy to create out of something like a microcontroller. The digital logic is inherently 2 voltages internally. So if we want to get a PWM signal, we just take one of those output pins and control how often is it 1, how often is it 0. Just changing the timing is all we need to do to get continuous valued output. So PWM is very cheap. It's much cheaper than building a digital analog converter, which requires all kinds of analog circuitry that has to be carefully matched. PWM is also fairly fast. It requires very little internal control, just something to take care of the timing. And timing is one of the easiest things to do in digital logic. So PWM is cheap, one advantage. Another advantage is that it's very robust. If we take a PWM signal and run it through a wire in an industrial environment where there's a lot of electrical noise and stuff going on, we don't have to worry too much about the noise that gets added to that signal, because when we get to the other end of the wire, we can run the thing through something like a Schmitt trigger. And as long as the noise is not so enormous that it completely wipes out our signal, we can clean up the signal and come back to almost exactly the same thing that came in. The nice thing about having only 2 voltage levels is that if you add a bunch of noise to them, as long as the noise isn't so much as to take you from one level to the other, you can clean it up with something like a Schmitt trigger. So we've got a very robust signal here. We can recover the analog value, the continuous value that's represented in the PWM signal, with just something as cheap as a Schmitt trigger. How do we convert this thing if we do need it as a continuous voltage, though? If we really need an analog voltage for some purpose, is there a way to clean up the PWM signal to get that continuous voltage out when what we've got is just two voltage values? And the answer is, of course, it is possible to do that. And there's a couple different ways one can do it. One thing that's used a lot in things like motor controllers is to not basically do anything. Because we've got a voltage signal that's swinging here up and down, possibly quite a large voltage. So that's our PWM signal. This is our delta T. But let's take a look. What's the current doing? Well, if we're driving an inductive load, then when the voltage is high, we're going to drive the current up, and when the voltage is low, we're going to drive the current down. And the current will have a sort of a triangle wave look. But if we've got a very large inductor, the slope of this is small. And that means the current doesn't change very much in the short time here. So if our PWM frequency is high enough, then what we end up with is the current just has a little ripple in it, not huge changes in current. And for a lot of things like motors and loudspeakers, the current is really what we care about in terms of what's driving the magnetic field that's causing the motion. So a lot of times you can put PWM signal directly into your motor or your loudspeaker, and that's it. You're done. The small changes in current gives you very little. Basically, the inductor itself is doing the PWM to analog conversion for you. That's not the only way to do it, though. If we look at this thing in the frequency domain, so if we say, well, how much energy do we have as a function of frequency? Well, we have an energy at 0 that corresponds basically to what's the average of this signal. Basically, this low frequency stuff here is the signal that we're actually looking at. But we have artifacts here at the PWM frequency. Oh, I didn't give you that term before. The PWM frequency is just 1 over the PWM period. So at 1, at 2 at 3 times FPWM, and so on, we'll have energy. In fact, most of it's going to be in the odd harmonics, because if we had a square wave here, we'd have energy in just the odd harmonics, because it's not a perfect square wave, it's a rectangular wave. We'll have some of the even ones as well. If we wanted to get just the signal, which is all at low frequencies, and get rid of the high frequency stuff here, well, notice that this was a discrete time. So we've got the standard Nyquist theorem results that says anything that's less than half our sampling rate, so less than half of FPWM, is the signal that we really want. Anything above that is going to get aliased to something as if it was lower. So we just need to put in a low-pass filter, just like we would for any other digital to analog conversion, to get rid of stuff at the PWM frequency and higher. And what we will be doing when we use PWM for our Class D amplifier is to use both of these techniques. The thing that we're driving in the Class D amplifier is a loudspeaker, which is basically an inductive load. And so we'll be getting a lot of averaging here from just using the current rather than the voltage is what's really driving the loudspeaker. But we'll also put in a filter so that even the voltage doesn't change much. So we'll have the pulse width modulation signal coming out of the Class D amplifier. We'll run it through a filter that smooths it out quite a bit, and then the fact that there's an inductive load smooths that out even more. And so we'll have very little fluctuation, very little high energy at the high frequencies, and just the audio signal that we're trying to get to the loudspeaker going through. That's really all you need to know about pulse width modulation for now. We'll do another video on how to create a pulse width modulation signal, and we'll do some on the Class D amplifier using the pulse width modulation signal. But the basics are all here.